Okay, let's wait for 5 more minutes. Let's see. After that, we will start. Okay, so let's start with today's class. So, good evening, everyone. My name is Amit Kumar Sharma, and today we are taking live session class 6 for week 6 content for the course Energy Conservation and Waste Heat Recovery by the course instructor Professor Prashant Kumar Das and Professor A. Bhattacharya from IIT Kharagpur. Okay, so as of now, we have covered up to week 5, and today we are covering week 6 course content. So, as you all know, that every week we are having a live session on every Friday from 7 p.m. to 9 p.m. So basically, in this live session, we discuss previous week's sample question, and we discuss those questions in class, and we thought that this question is going to be very helpful to you in your upcoming assignments. And this class is being recorded, so the PPT that has been shared in this class, and also the class recording will be provided to you from the NPTEL team. So I hope you will learn a lot from this session, and in this session we interact each other, so it's good to join this session. So I hope those who are not joined in today's class, maybe they will join in next week's class. Okay, let's start with today's class. So the first question is, identify the correct statements regarding a rotary regenerator. So we have seen different types of heat exchangers. So this is also a type of rotary regenerator. So we have to identify the correct statement regarding that. So we have four options. Option A, it is used only for gas to gas heat exchange. Heat exchange. B, it is used only for gas to liquid heat exchange. C, it can be used for any kind of fluid pair, and it contains a storage matrix. Take 2-3 minutes to think about it. So, okay. Any guess, Sebas? Any other student? Any guess?
Sir, BD, sir.
Okay, B and D. Okay, let's see. So, rotary regenerator. So, basically, in this, we use a wheel or drum that rotates, and there is a type of a storage matrix. Through that, we flow the fluid, and it get so the heat get exchanged. So basically, so it contains the storage matrix. So D is correct. It seems correct. Okay. So, but it is only used for gas to gas heat exchange. Okay, because the matrix, because it is rotating, and like complete it is completely rotating. Okay, so if we use liquid and heat, and it is completely having matrix. So suppose, so one side we are supplying the hot stream, and from other side we are supplying the cold stream. Okay, so this wheel is rotating. So suppose this matrix part is facing the hot fluid, but after rotation it will face the cold side also. So mostly it will be used only for gases. Okay, so that it will be very easy for the streams to get their heat exchanged. Okay, so in this way it contains the storage matrix, and basically it is used for gas to gas heat exchange only. So the correct option will be A and D. If we use liquid and gas, then we cannot have a rotation, because if you are using two type of medium, then there will be more complexity in the system, and it will not work. Okay, and for more detail, maybe you can also refer to the class notes. I think it's clear. So it is the rotary regenerator is used for gas to gas heat exchange, and it contains a storage matrix. identify which of the following statements or statement is or are true for regenerator with a rotary hood. So we are having four options. It is used as an air preheater. It has a fixed matrix and fixed streams of gases. It has a rotating matrix. None of the above. Try to recall class notes. So the correct answers are A and B. So basically, we use rotary heat generators with rotary hood for air preheater, because we know that in previous question also we have seen that this type of regenerator are basically used for gas to gas. Okay, so it is a very good heat exchanger for air preheating, because with the exhaust gas we can heat the incoming air for the combustion purpose. So it is used as an air preheater, and also it has a fixed matrix and fixed streams of gases. So here the stream will be fixed and the matrix will also fix. So only the hood is rotating. The matrix is going to be fixed. Matrix is not rotating. So the C is wrong and D is also wrong, none of the above. So the answer is A and B. So the statements which are true for rotary for the regenerator with rotary hood, it is used for air preheater and it has a fixed matrix and fixed stream of gases. Identify the correct statements regarding a run-around coil system. A run-around coil systems. So the first is it consists of two heat exchangers and need extra auxiliary power. It is suitable for heat recovery in air conditioning system. It should be used only when the distance between the hot and cold stream is large, and all of the above. So basically these are theoretical questions. So for these types of questions, you should always see the complete videos of the class and you try to also see the notes of the class, so you will be better understand these types of questions. So try to recall the class notes for a run around coil system and just take 2 minutes to answer it. So let's see the answer. Do we have any answer? Anybody? Okay. So the answer is option D. So basically all three options are correct, all of the above. So it consists of two heat exchangers and need extra auxiliary power. So basically in run around coil system, there are two heat exchangers. Okay. So or maybe you can say it is supply, or this side it will be exhaust, and the connection are like this. We're using a pump here. Okay, and one another line is also there. Okay. So basically it consists of a pair of fin tubes coil which recover warm air from the exhaust airstream. Okay. The pipework system usually distribute water which transfer the heat between the two airstreams, and the pump circulate the water. So basically here you can see we are using a pump. So in option 1 we can see it needs extra auxiliary power. So yeah, we need extra auxiliary power to maintain the pump. It is suitable for heat recovery in air conditioning system. So here we are having systematic of two types of supply and exhaust. Okay. So we can use it for the air conditioning. It should be used only when the distance between the hot and cold stream is large, because you can see we are using piping network here. So it is very suitable for a long distance between hot and cold stream. So with the suitable piping, in that piping we can flow the water, and from water we can supply we can exchange the heat as the water is a medium. So basically all three options are correct. So it consists of two heat exchangers. You can see here. It is suitable for heat recovery in air conditioning system. It should be used only when the distance between the hot and cold stream is large. So the correct option is all of the above. Calculate the minimum amount of hot utility for a heat exchanger network for which the temperature values of hot and cold streams are given in the table below. Take delta T minimum as 20 degrees centigrade. So this is a numerical, and a very good numerical, in which you have to find out the minimum amount of hot utility for a heat exchanger network for which the temperature value is given. Okay, you have to take the delta T minimum as 20 degree. You have given hot stream, cold stream, their heat capacities. For hot stream 1, it is 2. For hot stream 2, it is 8. For cold streams 3, it is 2.5. For cold stream 4, it is 3.0. Then source temperature 170, 120, 30, 20. And target temperature 70, 70, 125, 130. If you try to recall the class lectures, so maybe you will be know you will be knowing that uh, there is a complete a single class, I think, on this topic. So try to recall that class and try to solve this question. So for this you can take 3-4 minutes. After that we will see the solution. So for a hint, try to make this table. So in this, we have to make the cold stream and the hot stream. Okay. Mention all the known temperature that are known to you. And we have given the delta T minimum temperature difference. So based on that, you have to find out the other temperatures and try to always maintain a minimum difference of 20. Okay. Try to recall this now. Okay. So let's see. So we have given for hot stream, the source temperature are we have 170, 120, 30 and 20. So it is 170. So here you can write 170, then 120, then 30, 20. Okay. So here 30 and 20. So 30, 20. Okay. This side source temperature and target 70, 70, 125, 130. We can see 70 and then 125 and 130. Okay. So with this there's 170. Okay. Then we are coming to 130. So here we know that del T minimum is 20 degree. So maximum temperature difference will be 20 degree. Okay. So from 170, if we go downward, so it will be minus 20. It will be 150. Okay, 150. Now we are having again 125. So again 125. So again we have maximum 20 degree temperature difference. So 125 plus 20 will be 145. So it will be 145. So there will be 150 to 145. Now we have 120. So again this temperature will be minus 20. Difference can be there. So it will be 100. So now we are having this temperature 70. So this will be 70 minus 20 will be 50. This 30. So minus 20, 50, and like this 20, 40. So you have to draw this. Okay. So we are having cold streams, hot streams, and now we are having their temperatures. So for more detailed, you can refer the class videos. In that, the professor has undertook this topic very seriously and they have shown in detail. I think a complete class is there for this pinch point and this stream temperature exchange and all. So after the calculation, for the calculation, you can see the class notes. Okay, so you have to minimum amount of hot utility we have to calculate. After the complete calculation, so this is the answer for hot utility. It will be 52.5, and for cold utility it will be 85. So 52.5. So the correct option will be option C. Okay, so the hot utility will be option C. Answer is C. So basically, first draw a table of complete subnetwork and cold stream temperatures, hot stream temperature. Try to find out all the possible temperatures. Then again make a separate in which you have to draw the deficit, accumulated, and the heat flow. After the complete calculation, you will get to know the hot utility and the cold utility. Now the calculate the minimum amount of cold utility for the heat exchanger reactor given in the question number 4. So in like previous question, so we have calculated the 85 will be the answer. It will be the 85 answer is B. So the solution is B, and the complete for the complete explanation. Solution of question 5 is the solution of question number 4. So the previous solution we can see. So yeah, in this we have seen both. We are having hot and cold utilities. Now calculate the pinch point temperature for both hot and cold stream for heat exchanger network given in the question number 4. Again, we have to calculate the same question. So this question basically, this complete calculation is not only for one question. There are multiple questions linked to this calculation. Okay. So the hot will be 120 and the cold will be 100 degree. 120 and 100. So that we can see from here. So this is your pinch point temperatures, 120 and 100. Okay. So in a 1 to 2, so let's come to the next question. In 1 to 2, TEMA E-shell and tube exchanger, water enters the cell at 30 degrees centigrade at a rate of 1.8 kg per second. Engine oil flows through the tubes at a rate of 1.3 kg per second. The inlet and outlet temperature of the oils are given 180 degree and 110 degree centigrade respectively. The specific heats of water and oil are 4.19 and 1.67 kg per gram Kelvin respectively. Overall heat transfer coefficient is 225 watt per meter square. Assume the hot fluid side fouling is negligible. Find out the correction factor. So the diagram is given for the correction factor. The figure 1 shows the correction factor is a ratio of PY and RI. So try to find the answer. Just take 2-3 minutes, then we will see the solution. It's quite a big question. So first of all, try to note down all the data. And the answer is B. We will find out how the answer is coming. So first try to note down all the data. After writing the data, try to recall the class notes and then try to solve it. So the main data is like what type of heat exchanger? It is cell and tube. Okay. And water enters the cell temperature in the flow rate. And the oil flow rate is given. Inlet and outlet temperatures given. The specific heats of water and oil given. So note down these data. Okay. After that, you will get to know that how to apply the formulas. So you have also given the overall heat transfer coefficient. Now assume the hot fluid side fouling is negligible. So we have given a lot of data. When there are a lot of data in the question, so don't try to get confused with these data. Try to note these data down and in the notebook, and after that maybe you will recall how to solve this. Okay, so anybody is trying to solving it? Shehbaz?
Yes, sir.
Okay, try. I think we have a meeting guest. Do you want to introduce yourself? Your name is not coming. Okay. Just wait one more minute. If you have any answer, let me know. Okay. So first of all, as they have mentioned cell and tube. Okay. So first of all, draw a basic schematic. So first we will draw a cell. So okay, and a tube. This is a tube. So this is a tube, and this is your cell. The entry to the cell is here from water is entering from this side and outgoing from this side. For tube, the oil is entering from here, and you can see it's flowing like this. Okay, as the shape of the tube, and it is having the his exit from this side. So the temperature of water we have given 30 degree, and also the mass flow rate 1.8 kg per second. Okay, uh, and we have given this Cp 1.67 is for the specific heat of water is 4.19 and the oil is 1.67. So specific heat of oil 1.67, specific heat of water is 4.19, and the fouling factor, sorry, the overall heat transfer coefficient is 225 watt per meter square Kelvin. So always whenever equation like this is coming, try to first draw a basic schematic. Try to draw where is the input of hot stream, where is the exit of hot stream, where is the input of cold stream, where is the exit of cold stream, and each stream try to note down their respective properties. Like what is the temperature there, mass flow rate is there, okay, Cp is there. After that, you will get to know how to solve this. Because if we read data from this question directly, it is confusing. Now, if you see this, it's quite it looks quite easy. So now now first of all, you should find the heat capacity rates. So heat capacity rates for the cell fluid water and tube fluid oil. So it will be CmCp, mass flow rate into heat capacity. So for the water, it will be mass flow rate of water 1.8 kg per second multiplied by 4.19 into 10 to the power 3 joule per kg Kelvin. And always try to use the units also, because suppose if the flow rate is in gram per second and you directly put 1.8, then your answer will be wrong, and maybe it will be in kilojoule. Okay, so always try to make the same unit balance is also very important. So you will get the heat capacity as 7542 watt per Kelvin, and for oil it will be 1.3. Okay, so the flow rate of oil is 1.3 kg per second into 1.67 into 10 to the power 3 joule per kg Kelvin. So after solving, you will get 2171 watt per Kelvin. The first step is find the heat capacity rates. Okay. Now find the heat transfer rate from the coil, from the oil. Okay. Sorry. So the Q will be heat capacity into temperature difference. So we have given the inlet temperature is 180 degree, and the outlet is 110. So 1110, okay, 110 degrees centigrade. So it will be 217 watt to 2171 watt per Kelvin. 180 minus 110. After the calculation, it will come around 151.97 into 10 to the power 3 watt. So we know the inlet and the outlet condition for hot stream oil. So from that, we can find the exact heat transfer. So this much amount of heat is taking part in the heat exchange. So the oil will lose this amount of heat and the water will gain this much heat. Okay. So apply the energy balance. Now Also apply the same formula for water, and now the heat will remain same because we are considering heat loss as a zero. So this complete heat that is given by the hot oil will go directly to the water. So the temperature of oil is decreasing from 180 degree to 110 degree centigrade, and the water is increasing from 30 degree to suppose X. Okay, so apply the energy balance, just write the same formula for water and solve it. So you will get okay T plus Q upon heat capacity. If you like again transfer this T that side and multiply this, so you will again get Q C delta T. Now Q we have as like this, C we know for water, del T we know T minus T, it will be the T out minus T in. So based on that you will solve it and you will get 50.15 degree centigrade. Okay, so temperature is 50.15 degree centigrade. So first we have found out the heat capacity. After that we know the temperature difference of hot stream. So calculate the heat transfer rate. Based on that heat transfer rate, calculate the temperature of the cold stream, extreme temperatures. Because we have given only the inlet temperature, we have not given the outer temperature. So based on the heat transfer rate, we have calculated the outer temperature. It will be 50.15. So it will be 50.15 degrees centigrade. So the diagram of, you can say the heat exchange is like this. So 180 degree to 10 and 30 to 50.15. So you can see the oil is coming like this from high to low, and the water is going like this. Okay. So now calculate del T1. So del T1 will be this one. So 180 minus 50.15. Del T2 will be this one. So it will be 110 minus 30. It will be 80. So calculate the log mean the LMTD. So it will be del T1 minus del T2 upon ln del T1 upon del T2. If you put all the data, it will come like this, 102.92 degree. Now calculate the P and R. You know the formulas. Okay. So the P will come like 0.4667 and R will be 0.2878. So you have this P1 line. Okay. And these are the R lines. So intersect. Now find out the point where P is 0.4667 and R is 0.2878. So the F line, so this is the F line. Okay. So find the first R 0.2878. So you can see this is 0.2 and this is 0.3. Okay. And the P is 0.4667. So for R, the line is near like this here. Okay, it will go like this. Okay. Now see the value of PI. It is 0.4667. So it will be like here, 4.4 and 0.5 like here. Okay. So again, it will go like this. So it will meet near here. So you will also get a table in this exact values will be there. So from that table, because from the graph, it is difficult to locate the point. So it will be around, you can see the 0.98 will come here. So approximately we know that it will be in this region, but for exact value, you will also get a table. In that, the values with the P and R will be given. So based on that, we can find out the F will be 0.98. The correction factor is 0.98. So the question like It's quite difficult. Seems initially very difficult, but if you see the solution, just very easy. You have to calculate the heat capacity rate, then heat transfer rate. Based on that, you have to calculate the outlet temperature of the water, or you can say, suppose if they have given the water outlet temperature, then maybe you have to calculate the oil outlet temperature. So basically, the funda is that try to calculate all temperatures. The inlet of you can say the both end temperatures of hot stream, both end temperature of cold stream. Okay, you know the heat capacity, find the LMTD, apply this formula, and use the graph and table. You will get to know the answer. I think it's clear. Any doubt? Okay. The next question is again for the above problem. Find out the mean temperature difference, MTD. So you have this again same problem. Okay. So I think you have noted down the data, or maybe you can see the data again. I think this data is enough for. So you have to find out the mean temperature difference, MTD. Yes, Abbas, do you want to say something?
No, sir. No, sir.
Okay. So you can. So the temperature, you have to find out the mean temperature difference, MTD. Maybe I think you have the fouling factor at 0.98 and you know the data. You can take maybe 1 or 2 minutes to find out the mean temperature difference. Here you can see the data. Any answer for the mean temperature difference, MTD? Okay. So it's quite simple. MTD is basically F into del T LM. Okay, MTD is F del T LM. So we know the F, it is 0.98, and we know the del T LM is 102.92. So just multiply these and you will get 100.86. It is this. Okay, so the question number 8 is directly linked with the question number 7, because if you don't know the F, then you cannot calculate it. So basically this solution is very important. Okay, if you know the solution, you can get 2 correct questions. So now for the above problem, question number 8, find out the surface area of exchanger by mean temperature difference method. So now again, the question is again linked to previous question. Now you know the MTD. Now based on that, you have to find out the surface area of heat exchanger. So this is the MTD. This is the data. Okay. Let me know if you need data to show. So yeah, this is the data. Now find out the temperature difference. Find out the find out the surface area of the exchanger by MTD method. So basically you have your MTD, you have F, and you have all these data, and you have also given overall heat transfer coefficient U. Okay, maybe you can note it down for solving this question. 225 watt per meter square Kelvin. So you have this data. Maybe just see for 10-20 seconds. If you need any other data from this question, you can put it down. Okay. So if you want to note out any data, note down any data from this slide, you can note it down. That will be going to help you in calculation of the area of heat exchanger surface. Let me make it clear. And also see this slide. So MTD is also we are having like this. I think now you can just take 2 minutes to solve this. It's very simple now. Just you have to recall a formula. You know all the data, and you have to just you have to do the calculation. Okay, so let's see the solution. So we know that the actual heat transfer from a heat exchanger is like Q equals to U F A del T L M. Okay, so you need to calculate the area A, then you have to just transfer the rest of the U F and del T L M into the denominator of the Q. So A will be Q upon U F del T L M. After putting these values, you will get the area. Always again try to like always remember units. These are very important. Okay, you should try to handle with care with the units. It will be 6.7 meter square will be the area. So for the above problem, we have found out the area is 6.7 meter square. So now again, this question is also linked to the previous question. Okay. So now you know the LMTD, you know the MTD, you know the area. Now calculate the effectiveness of heat exchanger. So you can see these questions are very linked actually. So you have to understand every question very carefully because the next one may be linked to that one question. Okay. So I think you have the previous old data. Now just take this data. 6.7 meter square is the area and try to calculate the effectiveness. Take 2-3 minutes. So do we have any answer? Okay, just take 1 more minute. Okay, so let's see. So if you recall from the heat capacities that we have calculated, so these are for water, for oil. So we can see the heat capacity for oil is less than water. So we are going to use this. So the oil capacity is lower than the water. So using the definition of effectiveness of tube side, that is C minimum. Okay, we get this formula 180 minus 110 upon 130, 180 minus 30. So we will get the effectiveness is 0.667, 0.4667. So to find out the minimum side of effect, the heat capacity C minimum. Okay, so it will be 180 minus 1110 upon 180 minus 30. The maximum temperature difference in the bottom and the minimum capacity rate, that is for the oil, that heat transfer, is going to be the answer. So it will be 0.4667. The answer is option D. Again, this question is linked to the previous one. So you can see for this topic, you should know the every question. Okay. For the above problem, question number 10, find out the heat transfer unit NTU. Now you have to find out the NTU, net heat transfer units. In the table given below formula for finding out NTU, we have also given the formula this time. Both different flow arrangements are given. So you have given a arrangement. So maybe I will show you the slides from here for 10 seconds each. Maybe you can try to remember the required things to solve, to find the NTU. You can write which types of heat exchanger it is. It is mentioned 1, 2, TEMA, E, shell and tube exchanger. So take a quick look to note down the required data that can be useful to calculate the NTU. Okay, note down any data from this slide also. Okay, note down data from this slide. Okay, you can note down any data from this slide like MTD. From here, you can note down the area. From here, you can note down the effectiveness. I think now you can calculate the NTU. Apply the respective formula and let me know the answer. I think you have to apply this formula. Do we have any answer? Okay. So we have given the formula for NTU, that is 1 upon D ln 2 minus effectiveness, say eta 1 plus C double dash minus C star, you can say minus D, or upon 2 minus epsilon 1 plus C star plus D. So this is the formula, and you have to find out the C star, that is the heat capacity of oil and water. It's going to be 0.2878. Then find out the D, 1 plus this C star to the square, and to the complete square root. It's going to be 1.046. Now put this in this formula, so you will get the data answer, and TU will be 0.696. You can see the options. So the NTU is 0.696. Okay. So we have seen that one question was linked to around 4 questions. So this 7 question, question number 7 was linked to question number 7, then 8, then 9, then 10, then 11. Okay. So now question number 12. Recuperators are direct transfer type heat exchangers which fall into the category of indirect contact heat exchangers. We are talking about recuperators are direct transfer type heat exchangers which fall into the category of indirect contact heat exchangers. Which of the following statements are correct for the recuperators? Or statement is correct for the recuperators? Statement A is there is no direct mixing of the two or more fluids because each fluid flows in separate fluid passages. Heat transfer continuously from the hot fluid to the cold fluid through a dividing wall. Some examples of recuperators are tubular, plate type, and extended surface exchangers, and all of the above. So take 2 minutes, go through all the four options, and let me know the answer. Hey, do we have any answer?
Answer D, sir.
Yeah, nice. So the correct option is D because we know that in recuperators there is no mixing, there is no direct mixing, okay, of the two or more fluids because each fluid flows in their separate fluid passage. So they are having tubes, okay, and shell you can say also. So they are having their own passages. Heat transfer continuously from the hot fluid to the cold fluid through a dividing wall. There is a dividing wall. There is no direct contact. Some example of recuperators are tubular, plate type, and extended surface exchangers. So the correct options will be all of the above. Option D is correct. Regenerators are storage type exchangers falling into the category of indirect contact heat exchangers. Which of the following statements is or are correct for regenerator? Statement A is heat transfer is continuously taking place without storing thermal energy. B, corresponding thermal energy is alternatively stored and released by the matrix wall. Compact surface area density and the counterflow arrangement make the regenerator ideally suited for gas-to-gas heat exchangers application requiring high exchanger effectiveness. Option D is a compact regenerator usually has a smaller volume and is lower in weight than an equivalent recuperator. Go through all the options, take 2-3 minutes. Do we have any answer?
BCD, sir.
Okay, let's see. So the answer is B, C, D. Nice. So regenerators are, we know that types are storage type heat exchangers. Okay. So because these are storage types, so the option A is directly wrong because it is saying that heat transfer is continuously taking place without storing thermal energy. But in this, we are storing thermal energy and then exchanging heat. A is wrong. Corresponding thermal energy is alternatively stored and released by the matrix wall. So we are using matrix. We have also seen in, I think, in our first question. So we are using matrix in these. We are storing thermal energy and then we are exchanging it. B is correct. Compact surface area density and the counterflow arrangement make the regenerator ideally suited for gas to gas. We have seen that it is for gas to gas heat exchangers application regarding requiring high exchanger effectiveness. C is also correct. D, a compact regenerator usually has a smaller volume and is lower in weight than an equivalent recuperator. So it is also there because if we are using a compact, then weight is going to be small. Okay, and it is equivalent to be the recuperator. So B, C, and D are correct. Which condition should be satisfied for hot and matching in pinch analysis? So we have try to recall the pinch point analysis and try to find out the correct answer. Pinch point analysis, we have also done a numerical today, and it is very important topic in context of heat exchanger. So try to find out the correct conditions for pinch analysis. Do we have any answer?
AC, sir.
A, nice. So the answer is A and C. So the number of hot stream should be lesser than the or equal to number of cold stream. So this is the first condition. And the other condition will be heat capacity rate of hot stream should be lesser than or equal to heat capacity rate of cold stream. So these are two conditions. You can also question number 14 for lecture 36 and this time. So there is a detailed solution is also there. Okay. So basically, that conditions are number of hot stream should be lesser than or equal to number of cold stream, and the heat capacity rate of hot stream should be lesser than or equal to heat capacity rate of cold stream. Which condition should be satisfied for cold end matching in pinch analysis? So earlier was for hot end matching, now this is for cold end matching. Take 2 minutes. Try to recall the pinch analysis. Do we have any answer?
Sir, BD, sir.
Okay, nice. The correct answer is B and D. So for the cold end matching, the number of cold stream should be lesser than or equal to number of hot stream, and the heat capacity rate of the cold stream should be lesser than or equal to heat capacity rate of hot stream. Okay. So these were the question for the previous week. So let me again just repeat from question number 1. If you have any doubt, we can discuss further. Otherwise, let's move to some theoretical part, because still we have around 30 minutes. So quickly we can revise. So I think it was just theoretical rotary generator. It was also theoretical question about the regenerator. Answer was A and B. It was about the runaround coil system. Okay. So the all statements are correct. So this is the question regarding the your pinch point analysis. So multiple questions are connected to this. Okay. So you have to make the table first. Then you have to calculate the deficit, accumulated heat and heat flows required. Okay. Based on that, you will find out the values for your pinch point and the required hot utility and the cold utility. And the amount of cold utility. So the question from that question, you know the answers. Yeah, again in this multiple questions are connected. So as we have mentioned earlier, that try to draw a basic schematic like this, mention all the end states, all the data points. After that, go step by step, calculate the heat capacity rate, calculate the heat transfer rate, then calculate the remaining temperature difference of the endpoints, draw the diagram. Okay, now calculate the LMTD. So from the graph and the table, calculate the value of F. Then you have F, you have LMTD, calculate the MTD. Now you have MTD, F, LT, Q, U, calculate the area required. You have the area, so calculate the effectiveness. The temperature also. So you can convert the effectiveness of the heat exchanger. Now apply the formula for NTU. You can calculate the NTU, okay, using the formula and the data. Now, so you can see from one question we can calculate up to 4 to 5 answers. Okay. So now this again theoretical question about the recuperators. So the answer is all of the above because we are using direct. There is no direct mixing. The heat transfer continuously from the hot fluid to the cold fluid. And some examples of recuperators are tubular, plate type, and extended surface exchanger. Again, a theoretical, theoretical. Okay. So just let quickly revise about heat exchangers. Okay. So to analyze heat exchangers, so a set of assumptions are there. Okay. So these assumptions are we have to consider a steady state operation. Okay, so whenever you can see we have solved two numericals also. So whenever we are solving these, in actual there will be dynamic conditions, but for sake of calculation, we consider steady state condition. Heat loss to and from surroundings are assumed to be negligible. That's why we are considering that the heat given by the hot fluid is complete heat taken by the cold fluid. So we are not considering any heat loss. There are no thermal energy source or sink in the exchanger walls or fluids such as electric heating, chemical reaction, or nuclear power. So there is no such thermal energy source. Okay. Temperature of each fluid is assumed to be uniform. So we are also assuming the uniform temperature in a cross section. Wall thermal resistance is distributed uniformly. So these are some important points which we need to consider. So these are the important assumption whenever we are trying to solve the heat exchanger analysis. Okay. So means steady state operation. We have to consider the heat loss to and from surrounding negligible. And also the wall thermal resistance to is distributed uniformly. Temperature of each fluid is assumed to be uniform in a cross section, and there are no thermal energy source or sinks in the exchanger walls or fluids such as electric heating, chemical reaction, or nuclear process. Now there are some basic definitions also, like heat transfer. You can say the dq is u, temperature difference, and area u del T dA. This is for local. So for the complete, you can use q um A del Tm, where um is the overall heat transfer coefficient, Tm is the true mean temperature difference, MTD. Okay. We have used this formula in our questions. So this is the temperature distribution in counterflow exchanger of single phase fluid. Okay, so you can see the direction is this 0 to the length of heat exchanger. Cold fluid is flowing like this, hot fluid is flowing like this. So this is losing heat, this is gaining heat. This is the heat exchange. Similarly, if heat capacity of hot fluid is greater than cold fluid, if heat capacities are equal, you can see they are the difference is going to be same. If heat capacity of cold fluid is greater than the hot fluid, it will be like this. Now it's for a pedal heat exchanger. So for if this is the condition, you can see the difference. This is the temperature distribution in inlet and outlet of unmixed cross flow heat exchanger. Okay. So this is the inlet of hot fluid, this is the inlet of cold fluid. or this is the hot fluid. This is the outer temperature distribution and the cold fluid outer temperature distribution. You can see there's a little bit, not a fixed, little bit, you can say curvilinear approach of the temperature difference at the outlet for the unmixed cross flow heat exchanger. So there are some like important terminology are like M is mass flow rate in kg per second, Cp is specific heat of fluid at constant temperature, constant pressure, joule per kg degree centigrade, and T is the temperature of the fluid in degree centigrade, and del T is the temperature drop or rise of fluid across the heat exchanger. So you can see the red is hot fluid, this is the cold fluid, it is flowing like this. So the red part is diminishing and the blue part is emerging. So that this is the heat, this is cooling downstream, this is heating upstream. So now we have the F and LMTD analysis. So is the in the analysis of heat exchanger, total heat transfer rate Q is of primary interest. The log mean temperature difference LMTD, or it is written as del T LM for counter and pedal flow, is defined as this one. LMTD equals to del T LM del T1 minus del T2 upon ln del T1 upon del T2. The total heat transfer between hot and cold fluid in a counterflow arrangement is like this: Q equals to UMA del Tm. So I think in our numerical we have used this formula, and these also. So you can calculate the LMTD. Okay. So basically LMTD represent the maximum temperature potential for heat transfer that can be obtained in a counterflow exchanger. So there are also some special cases. In case of counterflow, if the both heat capacities are equal, okay, then what will happen? Then the quantity of del Tm is indeterminate, because you know that if T1 equals to this comes to be the similar, then it will become 1. Okay, then log ln1 is 0, ln1 is 0, and this will also become 0. So LMTD will be 0 upon 0, that is indeterminate form. So we can apply the L-Hospital rule. After again solving, you will get the Q is equals to UA TH minus TC. So this difference will be the del T1, del T2 or LMTD. Okay, for the special case of this. Sorry. Now for the LMTD for multipass and cross flow heat exchangers. So the LMTD shown in the previous slide is not applicable for heat transfer, and for cross flow and multipass. So for the if there is a cross flow or multipass, then this is the formula. Okay. So here heat actually transferred to the heat which would be transferred if the same cold fluid temperature was raised to the hot fluid inlet temperature. Hence, it is temperature effectiveness of heat exchanger. So we can calculate P, and it is going to be useful in the calculation of F. It is del Tc upon del T max. So the heat actually transferred to the heat exchanger, which would be transferred if the same cold fluid temperature was raised to the hot fluid inlet temperature. Okay. And the R we have to calculate like Cc upon Ch. So it is the ratio of mCp of cold fluid to that of the hot fluid, and it is called the heat capacity rate ratio. So where the delta TLMCF is LMTD for counterflow arrangement with the same fluid inlet and outer temperature. Hence, in cross flow, heat is calculated by introducing a non-dimensional number F. So we have to find out the value of F using this P and R. I think we have solved a numerical on this. We have to calculate the value of P, value of R. Based on P and R, we have to calculate the value of F. Now, F we can put in this equation. So F is basically a correction factor. a non-dimensional number which can be used to correct the exact heat transfer from the particular configuration. It will be Q equals to UAF del T LCF. You can see these are the data for calculation of F. Okay. The actual heat transfer is obtained by using energy given off by hot fluid or energy received by the cold fluid. So we know that this is the basic energy balance equation. Q equals to mCpH Thi minus Tho mCp cold fluid Tco minus Tci. So it is very important equation. Maybe sometime you will be given the Cp, Tc, Thi, Tho, Tc, and you have to find out this one. I think we have solved a numerical on this energy balance. So because you will be given maybe three temperature, you have to calculate the fourth one. Okay, you may have given all the four temperature, you have to calculate the heat capacity like this. So you can apply this formula. So if the CH is greater than CC, then THI minus THO is less than TCO minus TCI. If CH is less than CC, then THI minus THO is greater than TCO minus TCI. The fluid that might undergo maximum temperature difference is the fluid with minimum heat capacity. Let's say minimum. So the fluid that might undergo maximum temperature difference. So the fluid which is having the maximum temperature difference will have minimum heat capacity rate, C minimum. Because of the C minimum only there can be maximum temperature difference. Okay. So the maximum possible heat transfer is expressed as Qmax will be mCpC Thi minus Tci. Okay. So this mCp will be minimum. This is maximum. Now the heat exchanger formula. So it is Ch upon C minimum. I think we have also used this. So the minimum and the maximum temperature difference we have to use on the bottom side. Okay. And on the top with the hot fluid and the cold fluid this. The above equation is valid for all heat exchanger flow arrangements. The value of epsilon ranges between 0 and 1. If the effectiveness is known, equation provides expression of determination of Q. So now if we know the effectiveness, so the actual heat transfer will be epsilons mCp and Thi minus Tci. So this will be the actual heat transfer. If we know the value of epsilon. Okay. As number of NTU, so NTU it depicts the non-dimensional heat transfer size of the heat exchanger. Okay, NTU is AU upon C minimum. So after solving, this is the expression. So if again, if CC is less than CH, okay, so CC will be C minimum and CH is going to be C maximum. The result will be the same. So you can see the result. In case of parallel flow, a similar analysis may be applied to obtain the following expression. This is for the counter flow. This is for the parallel flow. I think okay. So you will get. I think if there's a question on the NTU and all, you will get a formula table maybe. Yeah. So there are special cases. If C minimum upon C max equals to 1, it means both capacities are equal. Then what will happen? Then this will be become easy. The effectiveness will be NTU upon NTU plus 1 for counterflow, 1 upon 2, 1 minus e to the power minus 2 NTU for parallel flow. And Cmin upon Cmax equals to 0, as in boiler and condenser for parallel flow and counterflow. So this become 1 minus exponential minus NTU and pi NTU. Okay. It will depend on the flow arrangement also. So these are two special cases. There is also some effectiveness chart, effective NTU chart. Okay. Now we are having approximate values of NTU and effectiveness for typical heat exchangers. Like for automobile radiator, NTU is in the range of 0.5, effectiveness is 40%. Steam plant condenser, NTU is 1, and effectiveness 63%. Regenerator for industrial gas turbine, NTU is 10, effectiveness 90%. And the regenerator for Stirling engine, NTU 50, effectiveness 98%. Now the regenerator for LNG plant, NTU is 200, it is effectiveness is 99%. So you can see the only for 1% increase, NTU has increased 4 times. Okay. So whenever we are designing the heat exchanger system or doing analysis, we have to consider this part actually, that for only 1%, do we need to expense, do we need to expend more amount of money to increase the NTU? Because if NTU is increasing, mean the size is increasing, your cost is going to increase. So it is not advisable to increase your NTU for just only for 1% increase. Okay. Now some for heat exchanger network. So there are some conditions, like in process plant, we have to install heat exchanger network, because where there are multiple units are there, multiple exhaust streams are there, and we need to get some heat from this process scheme. So there are some conditions, like many streams of heating need heating and cooling in process plant. That's why we need heat exchanger network, because there are many streams which need heating and cooling. Utilities like hot air, hot oil, steam for heating. Utilities like air, water, chilled water, refrigerant for cooling. So these are for cooling. Now the efforts to be made for reducing the use of utilities. So we are trying to make the effort so that we can reduce the number of utilities, or we can design a network in which the heat exchangers can directly interact and supply the exhaust heat to the inlet temperature, to increase the inlet temperature. This can be done by heat integration. We can do it is called heat integration. Heat integration implies that heat exchangers between the hot and the cold stream. So between the hot and the cold stream, the cold stream is interacting with the hot stream and taking away the heat. In this way, we can decrease the number of utilities. This reduce the use of utilities. However, the increase in the number of heat exchangers. So because if we are not using utilities, but we are using the heat exchanger, so it will increase the number of heat exchangers. Okay. Now the heat exchanger synthesis mean designing a network so that using minimum number of heat exchanger, the use of utilities can be also minimized. So if you are like planning to install a complete heat exchanger network, then our aim should be to design in such a way that we will use minimum number of heat exchangers and the minimum use of utilities. I think this type of diagram was shown by the professor. So the rule is that these are the cold streams, these are the utilities, these are the hot stream, these are the hot, these are the cold, these are the heat exchangers. Okay, these are the utilities. These are the cold utilities, these are the hot utilities. Okay, so the formula for number of utilities will be n minus 1, where n is the number of process streams, n1 plus number of utilities. And there's a pinch technique. So pinch technique is basically a logic-based technique. It is based on first and second law of thermodynamics. Important. It's based on first and second law of thermodynamics. So we are following the laws of thermodynamics. There is one hot utility and one cold utility of infinite capacity. So we consider that There is one hot and one cold utility of infinite capacity. Steady state operation is there. There is no restriction for matching the streams. There is no restriction. Okay. All heat exchangers are without any phase change and without any heat generation or reaction. And heat exchangers are assumed to be in direct contact and counterflow. So these are the different condition. Okay. So I think example is there. We have given hot stream. We have given cold stream. This detailed example has been explained already in the class. Okay. So for detailed in-depth understanding, you can refer the class notes. We have given the heat capacities. So like CP, it's 2, 8, 2.5, and 3.0. It is the temperature of the uh, supply temperature. It is 150. 90, 20, 25. Target temperature is 60, 60, 125, 100. So we can arrange these in this table. Okay. So it's 20, 25, 60, 90, 100. Okay. So you can see the stream 4 is from 25 to 100. This from 20 to 125. This is from 90, 60, 60 to 150. So the goal of heat exchanger network synthesis is that minimum utility, stream matching, number of heat exchangers needed, and end temperature of the heat exchangers. So these are the 4 goals to achieve. So we can draw a composite curve. We can draw all lines, all temperature exchange lines in a single network TQ diagram. Okay, you can see we can exchange the heat in this region. Okay, but for this region we require hot and cold utilities. So this is the hot utility and this is the cold utility. Now all the conditions are satisfied. So now you have to calculate. As we have also discussed, we have to maintain the delta T is 20 degrees centigrade. To find out the deficit, accumulated, and heat flows. Then again you have to do the, like, at this point we have found out 0, 0. Okay, our pinch point. So this is different and this will be different. We can represent like this. The upper part is hot end problem, lower part is the cold end problem. The rule is pinch point divides the heat exchanger network into 2 independent problems to be solved separately, like this. So this will be the hot end, this will be the cold end. No heat flows is allowed across pinch point, no cold utility to be used in the hot end, no hot utility to be used in the cold end, and the violation of 2 to 4 gives double penalty. If you are violating any of these, then you will get double penalty on your network. Okay, and design of each end should start at the pinch point. You have to start from the pinch point. So these are some point for pinch and matching rules. These are again some example. This is the hot end design. Okay, stream data at pinch. Okay. So basically from today's class, we have seen that heat exchanger network is quite very important, and the knowledge of heat exchangers can be very useful if we are talking about the heat recovery, if we are talking about the energy conservation and waste heat recovery, so because with heat exchangers only, we are able to recover the most of waste heat. Okay. So in this, we have to understand carefully the pinch point analysis and what is the minimum number of heat exchanger required and how to design that. So it's very important topic, and I think today we have solved so many numericals also. So I hope these are very helpful for you, and maybe this will also helpful in your upcoming assignment. So okay, I think uh, we have discussed enough about heat exchangers today. Okay, so next week on next Friday, again at same time 7 to 9, we will meet again, and I hope you will join the class. So for I think for today's, I think our time is about to complete. So thank you for joining. Thank you everyone for joining the session, and thank you who will be viewing this video online maybe. Thank you to those friends also. I hope next time you join the live session, or I hope to meet you soon. Okay, so I am stop sharing my PPT. Okay, thank you everyone. Thank you, Sebas.